Hi everyone, we are in section 11.2 now, talking about series. So last time we were talking about infinite sequences. Those are just lists of numbers, lists of terms. Now for this section, we're going to be looking at what happens when we start adding terms of these infinite sequences. So in general, if we try to add the terms of an infinite sequence, we get an expression a1 plus a2 plus a3, etc., all the way up to an infinite value. And this is called an infinite series. Okay. Or we'll just call it a series as well, because in this class, again, we're only dealing with infinite series. And this is denoted as the sum of a sub n, either with the notation of n going from 1 to infinity or not, just the shorthand, the summation notation there. Now, when we're adding up terms of a sequence to get a series, it's only possible to find finite sums for certain series, but not others. So, for example, if we have the series 1 plus 2 plus 3 plus 4 plus 5, etc., adding up just all the whole numbers, this will grow infinitely large as n increases, right? It's just going to keep adding higher and higher and higher. Whereas if we take the series 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16, etc., so just 1 over powers of 2, that, as n goes towards infinity, that actually becomes closer to 1. So to determine whether a general series has a sum or not, we consider what we call the partial sums. Okay, and the partial sums are just basically the portions of the entire sum. So S1 is just the first term. S2 is the sum of the first two terms. S3, sum of the first three. S4, sum of the first four terms, etc., etc. So S sub n, that nth partial sum, is just the sum of the first n terms in the series. Okay, and then notationally we write this as the sum from 1 to n of a sub I. Okay, so there is a difference between the series and the partial sums. The partial sums are just a portion of the series, because the series is infinite, so it goes on forever. So these partial sums form a new sequence, and that is S sub n. So that's a new sequence where it's listing out, right, the sum of the first term, sum of the second, sum of the first two terms, sum of the first three terms, etc., etc., etc. Okay, so given a series, let Sn denote its nth partial sum. Okay, so that's where S sub n is just the sum from 1 to n of a sub I. So of all those terms in the series, up through the nth term. Okay. If the sequence is convergent, so if the sequence of the partial sums is convergent, and the limit, as n goes to infinity, of those partial sums equals s, if that exists as a real number, then we say that the series is called convergent as well. Oops. We say it's convergent. Okay. So again, if the sequence of partial sums is convergent, that means that the series is convergent. Okay, and then approaches one specific value, s. Okay, so we add up all those terms and they get us to s. Or, if we have the number s, okay, sorry, that should be a lowercase t there. Or the number s is called the sum of the series. Okay, so if the sequence is divergent, then the series is called divergent as well. Okay, so we're looking at these partial sums for the sequence. Okay, so we're looking up to just the nth term, and if we get that the sequence converges, it approaches a specific value, then that means the series converges. Okay? Because that tells me, right, if I add up, my first however many numbers, right, I've got, 1 plus 1/5 plus 1/100th, whatever the case may be, and I add up, all these values up to 1 over a million. Whatever the case may be, if these all approach a value, say, 3, then that means that if I just kept adding all the way, eventually I would still be approaching 3, is in essence what's happening here. Okay, so as the partial sums approach a number, a finite value, the sequence approaches that value. And if the partial sums just grow infinitely large, then that means the sequence grows infinitely large as well. Okay? So suppose we know that the sum of the first n terms of the series is s sub n equals a1 plus a2 plus all the way up to an equals 2n over 3n plus 5. Okay, so say we had this nice concise formula for the partial sums, then the sum of the series is the limit of the sequence. So here we have, the sum, right, of that series, that's going to be the limit of that sequence. So take the limit of that expression, we can play around with this algebraically, right, multiply top and bottom by 1 over n, so that's just going to be 2 over 3 plus 5 over n. As n goes to infinity, right, that term goes to 0, so we're just left with 2/3. Okay. So in other words, that series, right, that infinite series would sum to 2/3, right, if we let it go on forever. Okay. Now, one important thing to note, this is not going to be typical. We don't normally get a formula like this that we can just work with, so it's not easy to find expressions like this, but what we are going to do next is we're going to start looking at some more well-known series, ones where we can actually come up with formulas like this so that we can work with them a little more easily. So the main one we're going to study right now is the geometric series. So the geometric series has the form a plus ar squared plus ar cubed, all the way yada 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 to ar to the n minus 1, etc. So the shorthand for it is written right here in the summation notation, okay, with a being non-zero. So basically what the geometric series does is it takes a term, a, and then it starts multiplying it by what we call the common ratio, r, and we multiply it by r, and that gives us the next term. We multiply it by r again, that gives us the next term. Multiply by r gives us the next term, etc., etc. Okay, so the question that we're going to answer right now is, when is the geometric series convergent? When is it divergent? And we're also going to work on getting a formula so that we can look at the geometric series a little bit more easily. Okay, so if we start at r equals 1, so what happens when r equals 1 here? Well, in that case, we have the partial sum is just going to be a plus a times 1 plus a times 1, right, etc., etc., all the way up until we have the nth term, but they're all just a's. So this is n times a, and as n goes towards infinity, that is also going to go towards infinity, right? Or negative infinity if a happened to be a negative number. So this would go towards plus or minus infinity. Okay. So what does that tell us? Well, that tells us that this sequence, this partial sum, goes towards infinity. So since the limit as n approaches infinity of the partial sum That does not exist, right? The limit just goes infinitely large. So since it does not exist, we say the series diverges. Okay. So let's separate this off. Alright, so that's the case where r equals 1. So we know the geometric series diverges if that ratio, that common ratio, is 1. What happens when it's not 1? Okay, so then in this case we have S sub n is a plus ar plus ar squared plus yada yada yada, okay, all the way up to ar to the n minus 1. Okay, and now what we're going to do, so this is not something that I would necessarily expect you to come up with on your own, but we're just kind of going through a sort of a proof here. So that's S sub n. We're also going to look at r times S sub n. So that's going to be ar plus ar squared plus ar cubed plus etc., etc., etc. Okay, plus ar n minus 1 plus ar to the n, right? Because we got one additional term being multiplied in there. So what we're going to do with these, and the reason we're doing this is actually we can use these to develop a formula. So we're going to subtract. So subtract these two. So we're going to take S sub n minus r times S sub n. So try to visualize what's happening here. So I'm going to take this whole first one minus this whole second one. Notice that almost all of these terms overlap. So I'm going to have ar minus ar squared minus ar squared, ar cubed minus ar cubed, etc., all the way up to ar to the n minus 1 minus ar to the n minus 1. All of those terms are going to cancel with each other, and all we're going to have left, when all is said and done, are just a and minus a to the r, actually a r to the n. So this is just going to be a minus a times r to the n. Okay. Factor out S sub n, that's 1 minus r equals a times 1 minus r to the n. And this now gives us a formula for our nth partial sum for a geometric series. Okay. So when r is not equal to 1, we have this formula here that the geometric series will obey. But let's look at what exactly is going on here, because if we know that it's not going to work at r equals 1, right? We can see that right here. That would give us an undefined value. It's not going to work when r is bigger than 1, right? Because if this one diverged to infinity, well, if you start multiplying by bigger and bigger numbers, certainly that's also going to diverge. So let's look at what happens when r is between -1 and 1. So in this case, so if r is between -1 and 1, then that means that Rn is going to go to 0 as n goes to infinity. Okay, so think about that. If I take r is a fraction, right? It's between -1 and 1. as I raise it to higher and higher powers, the fraction is actually going to get smaller and smaller and smaller, right? 1/2 squared is 1/4. 1/2 cubed is 1/8. 1/2 to the fourth is 1/16. As you raise it to a higher power, the fraction actually gets smaller. So that means r to the n approaches 0 as n gets towards infinity. So the limit as n approaches infinity of s sub n, okay, which is the limit as n approaches infinity of a times 1 minus r to the n, fix that, over 1 minus r. Okay, that we can simplify a little bit because in this case r and a are both constants. Okay, n is the only variable here in this limit, so we can actually split this up into two terms. So I'm not going to go through the nitty-gritty details of the limit with you guys, but that will be a over 1 minus r over 1 minus r minus a over 1 minus r times the limit, and all that's left is r to the n. Okay. And as n goes towards infinity, this whole value goes to 0. So that means that this is left as a over 1 minus r. Okay, so we can go ahead and conclude. We can say thus, when the absolute value of r is less than 1, the series is convergent with with the sum being a over 1 minus r. Okay, so this can be summarized at the top of the next page here. So the geometric series from 1 to infinity of a times r to the n minus 1, that is convergent if the absolute value of r is less than 1, and in that case its sum is a over 1 minus r. Okay, and if the absolute value of r is greater than or equal to 1, the geometric series is divergent. Okay, so in essence, as long as we're multiplying by terms that are going to be smaller than 1, right, the absolute value is smaller than 1, then that's going to allow the series to converge, right, because we're adding on smaller and smaller values, whereas if we add on larger values,